Oh, this is our optimal F1 race. I'm Brady Parris.
I'm Casey Katsouris.
I'm Nicholas Brown.
So for our F1 race, we chose Spa as our race to go with. Its total circuit length is 7 kilometers, and the fastest lap time is a minute and 44, which is about 104 seconds, is what we're trying to go for. Our primary goal is to compute and track an optimal trajectory that minimizes total lap time while satisfying physical limitations such as tire friction limits and track boundaries. More in the overview, our constraints that we're going for are the tire friction limits and our track boundary. We want to optimize a trajectory line around this track so we can improve overall lap performance. And we're using nonlinear programming for path optimization, and we're accounting for aerodynamic, frictional, and geometric constraints.
When simulating the track in MATLAB, so we're trying to essentially give MATLAB a path to drive on. What we did was we imported an image and then overlaid a 96 by 96 grid on top of it so that it could have a coordinate system. And what we did is we traced the center line of our track by selecting points, and then we would save that file and have MATLAB use a spline function. Next slide. On the next slide, you'll see that our points that we selected, you'll see that in turns, our point selection is way more dense because we needed more points to give it a more accurate uh, idea of what's happening in those areas. And then in the middle, you'll see the MATLAB spline kind of traces it and creates a track. And then on the right, you'll see the actual circuit map, which we're really close to. There's only minor mistakes in the turns where they're not as accurate.
Looking into the optimization methods that we used, we tried out single shooting, multiple shooting, as well as direct spatial parameterization. When looking at the results from the single shooting, the method starts off from the start line and continuously tries to adjust at each point, causing some errors to occur to build up over time. As you can see, it did not follow the track properly, leading to a lap time of over 200 seconds and an average speed of 124 kilometers an hour. The optimization method was not working properly for what we wanted, so we looked elsewhere. When looking at multiple shooting, we had a much nicer result where it actually followed the track limits and resulted in 119 seconds, as well as an average speed of 209 kilometers an hour. Looking at the speed telemetry, you can see there's certain points, for example, the second hump where the baseline initially brakes and then continue to accelerate, but instead it skips that all the way and exits it's a straightaway to minimize time. And it was fairly close to the minimum lap time at the record, but it didn't quite reach that point. So we decided to look into direct spatial parameterization because in particular with our track, it would help a lot in minimizing that lap time as it optimizes the path based on the geometry alone, using the track center line as a baseline and then adjusting the lateral shift to minimize distance and curvature. Now afterwards, we calculate the physics and implement that into the geometry that we calculated, resulting in a better lap time, but possibly more aggressive physics with very hard braking and acceleration having to be done to reach the geometry. Looking at the actual results, see the lap time reached 114.67 seconds and an average speed of 219 kilometers an hour, which is slightly faster than the multiple shooting. However, if you actually look at the curvature points, like the points in which it turned, they are very dark blue, showing that there was very aggressive braking going on, which could possibly cause issues with the actual physics of it. So the multiple shooting may have been a more realistic approach, but this results in a faster lap time overall.
In conclusion, the optimized lap that we have closely matches the expected strategy where it's braking preemptively before turns and accelerating out of them. The racing line we have, though, is not fully aggressive and optimal enough because of our single track width instead of the varying track width that F1 tracks actually have. We have limitations due to the trace of the track being inaccurate in some turns. We assume the constant track width, which it's not actually like that. And the constraint of keeping the point mass strictly within track bounds. In F1 racing, you're allowed to cut corners a little bit, and so we don't have as aggressive as a line. And our model overbrakes and under accelerates through some turns, which results in slower average velocity and a slower lap and a faster lap time, slower lap time. And for future work, we're going to improve our track tracing accuracy. So adding more points in turns to make it more defined for MATLAB. Incorporating a variable track width into the model will help for creating a bit more aggressive line. And then allowing for our simulation to cut corners a little bit according to F1 rules will also result in a more aggressive line. And then refining the braking and acceleration behavior because right now the over braking and under accelerating is through turns is reducing our speed considerably.